ASP.NET Core Demystified, Building Modern Web Applications from Concepts to Creation. Chapter 1, The Digital Canvas, Understanding Web Applications and ASP.NET Core. Imagine a world without the internet. No instant news, no online shopping, no video calls with loved ones across the globe. Our lives are intricately woven with the digital threads of the web, and at the heart of this intricate tapestry lie web applications. These are the engines that power everything from your favorite social media site to internal company dashboards. But how do they actually work? And where does something like ASP.NET Core fit into this complex digital landscape? To truly grasp the essence of web applications, let's use a familiar analogy: a bustling restaurant. The restaurant analogy: how the web works. In our restaurant, there are several key players and processes. You, the customer, the client browser. You're sitting at a table with a menu in hand, deciding what you want. In the digital world, you are the client, and your web browser, like Chrome, Safari, or Firefox, is your interface to the vast menu of the internet. You request something, perhaps by typing an address or clicking a link. The wait staff and kitchen, the server. When you place your order, you hand it to the wait staff, who take it to the kitchen. The kitchen efficiently prepares your meal. In our analogy, the server is a powerful computer system designed to receive your requests. It processes your order, your typed web address or clicked link, retrieves the necessary ingredients, data, and prepares your meal, the web page or information you asked for. The order slip and delivery system, HTTP. How do you place an order and how does the food get to your table? There's a specific process, a set of rules. This is like the Hypertext Transfer Protocol, or HTTP. It's the standard language for communication on the web. HTTP defines how your request is phrased, what information it contains, like your table number or special instructions, and how the server's response is formatted when it sends back your web content. The pantry and storeroom, the database. The kitchen doesn't conjure ingredients out of thin air. It relies on a well-stocked pantry. Similarly, web applications often need to store vast amounts of information: user profiles, product catalogs, order histories. This information resides in a database, the digital pantry that the server accesses to fulfill your requests. So, when you type www.example.com into your browser, you, the client, make an HTTP request for a web page. This request travels across the internet to the server. The server receives the request, processes it, perhaps fetching data from a database, and prepares an HTTP response. The server sends this response back to your browser. Your browser then displays the received content, the web page, to you. This fundamental request-response cycle is the bedrock of almost everything you experience online. From static pages to dynamic experiences, a brief history. Early on, the internet was like a vast collection of brochures. Websites were mostly static, pre-written pages of text and images. If you wanted to update something, you had to manually change the file on the server. There wasn't much interactivity. It was more like reading an online newspaper. These were our early restaurants, offering fixed, unchangeable menus. As the demand for more dynamic content grew, things like online forms, personalized content, and e-commerce developers needed ways to generate web pages on the fly, based on user input or data from databases. This led to the rise of server-side programming, where the server could execute code and build a unique web page for each request. Our restaurants started taking custom orders and offering unique daily specials. Today, web applications are incredibly sophisticated. They not only generate full web pages on the server, but also act as powerful digital service providers, delivering pure data to mobile apps, smart devices, and heavily interactive web pages that update in real time, often without needing a full page reload. Introducing Net and its evolution to NetCore. Before we dive into ASP.NET Core specifically, let's understand its larger family. Net. Think of Net as a powerful, general-purpose software development framework. It's not just for web applications. It's a massive collection of tools, libraries, and rules that allows developers to efficiently build many different types of software desktop applications, mobile apps, games, cloud services, and of course, web applications. If our computer science degree program had a general kitchen skills course, Net would be the comprehensive curriculum covering everything from baking to haute cuisine. For many years, the primary version of this framework was called Net Framework. It was robust and widely used, especially for building applications on Windows. However, as the world moved towards open-source technologies, cloud computing, and diverse operating systems, Linux, macOS, a need arose for a more flexible, modern, and high-performance version. This need led to the creation of NetCore. Imagine our traditional, highly specialized restaurant, well-established, but tied to a specific location, Windows only, and traditional cooking methods. NetCore is like launching a modern, adaptable, and highly efficient pop-up kitchen concept. It's cross-platform. No longer limited to Windows, applications built with NetCore can run seamlessly on Linux, macOS, and Windows. This means your kitchen can be set up almost anywhere. Open source. Its development is transparent and community-driven, fostering innovation and collaboration. Just like sharing recipes and techniques freely among chefs. High performance, optimized for speed and efficiency, making it ideal for modern, high-traffic web applications. It's a kitchen designed to serve many customers quickly during peak hours. Modular. You only include the components you need, making applications smaller and faster. Instead of a massive, pre-built kitchen, you assemble only the necessary stations for each culinary task. In late 2020, Microsoft unified all Net platforms under a single banner simply called Net. So, when we talk about Net today, we're building on the spirit and capabilities that NetCore introduced. What is ASP.NET Core's role? Within this modern Net ecosystem, ASP.NET Core is the specialized part for building web applications. If Net is the comprehensive set of kitchen tools and recipes, ASP.NET Core is the dedicated expert chef for all things web-related. It provides the specific libraries and components needed to build web APIs. These are the digital service providers we discussed earlier. They offer structured data to other applications, like a specialized menu for digital guests who want only raw ingredients or processed data, not a full-plated meal. Your mobile banking app, for instance, talks to a web API. Build web user interfaces. This involves generating the dynamic web pages that people interact with directly in their browsers. This is our restaurant serving full, beautifully presented meals directly to human patrons. This can range from simple data entry forms to complex, interactive dashboards. Whether you need to serve data to another application or present a full visual experience to a human user, ASP.NET Core provides the framework for orchestrating this interaction within the Net environment. Why ASP.NET Core for modern web development? Developers and organizations choose ASP.NET Core for a multitude of compelling reasons. Performance. It's blazing fast. Its design allows it to handle a high volume of requests, making it suitable for demanding applications. Cross-platform. The freedom to deploy your application on Windows, macOS, or Linux, and in various cloud environments offers immense flexibility. Unified experience. Whether you're building a web API, a traditional web application, or a real-time service, ASP.NET Core's consistent programming model simplifies development. Open source. The transparency and collaborative nature of its development mean constant improvement, a vibrant community, and access to the source code for deeper understanding. Robust security features. It comes with built-in mechanisms to help protect your applications from common web vulnerabilities, making it easier to build secure systems. Strong tooling and ecosystem. Backed by Microsoft, it integrates seamlessly with powerful development tools like Visual Studio and Visual Studio Code, and benefits from a rich ecosystem of libraries and community support. Modern architecture. It embraces modern software design principles, like modularity and dependency injection, which we'll explore later, promoting maintainability, testability, and scalability. Decades ago, building a dynamic web presence required intricate, often custom-built, solutions for handling everything from incoming requests to managing user sessions. It was a painstaking manual craft, like baking bread from scratch every time you made a sandwich. Modern frameworks like ASP.NET Core abstract away much of this complexity. They provide a sturdy, efficient kitchen equipped with specialized appliances and experienced staff, allowing you to focus on creating the delicious meals, the unique features and value your application provides, rather than constantly reinventing the basic infrastructure. This chapter has laid the conceptual groundwork. You now understand what web applications fundamentally are, how they communicate, and where ASP.NET Core fits into the larger picture of modern software development. In the next chapter, we'll conceptually prepare our developers' workshop, getting ready to explore the components that bring these applications to life. Chapter 2, the developers' workshop, setting up your ASP.NET Core environment. Every craftsperson, whether a carpenter, a chef, or a painter, needs a properly equipped workshop. They need the right tools laid out, a dedicated space to work, and access to the raw materials. Building a web application with ASP.NET Core is no different. While this book won't guide you through the intricate steps of installing software or typing specific commands, it's crucial to understand, conceptually, what makes up a developer's environment. Effectively, your digital workshop. The essentials for your digital craft. Imagine a chef setting up a new professional kitchen. They wouldn't just haphazardly throw ingredients and cooking utensils into a room. There's a methodical approach, ensuring every necessary piece of equipment is present and functional. Your ASP.NET Core development environment consists of a few core components, each serving a distinct purpose. The Net SDK, your core toolkit. Think of the Net Software Development Kit, SDK, as the comprehensive toolkit a skilled artisan carries. It's not just one tool, but a carefully curated collection necessary for building software. The SDK contains compilers. These are akin to instruction translators. You write your application's logic in C#, a human-readable programming language, and the compiler translates it into a language the computer can understand and execute. The Net Runtime. This is the engine that actually runs your compiled application. It provides the essential services and libraries your application needs to operate. Command Line Interface, CLI tools. These are your power tools for quick actions. They allow you to issue text-based commands to create new projects, install necessary components, run your application, or perform various development tasks. Libraries. These are pre-written blocks of code that perform common tasks, so you don't have to reinvent the wheel. Like having a pre-measured bag of flour or a specialized whisk ready to go. In essence, the Net SDK is the foundational layer. Without it, your computer wouldn't understand how to build or run an ASP.NET Core application. The Integrated Development Environment, IDE. Your professional workbench. While you could write your application's instructions, code, in a simple text editor, it would be slow and prone to errors, much like trying to prepare a gourmet meal with only a butter knife and a frying pan. This is where an Integrated Development Environment, IDE, comes in. An IDE is your professional, feature-rich workbench, tailor-made for software development. The two most popular choices within the ASP.NET Core world are Visual Studio. This is a full-featured, powerful workshop, especially prominent on Windows. It's often compared to a fully stocked, highly organized professional kitchen. It offers sophisticated tools for writing code, visually designing user interfaces, identifying and fixing errors, debugging, running tests, and managing large, complex projects. Visual Studio Code. A lighter, more flexible, and cross-platform alternative. Think of it as a versatile, portable chef's workstation that can be set up in any location, Windows, macOS, Linux. While not as grand as Visual Studio, it provides excellent capabilities for writing, navigating, and debugging code, especially when augmented with various extensions, add-ons that tailor it to specific development needs. Both IDEs provide features like syntax highlighting. Different parts of your code are colored, making it easier to read and understand. IntelliSense/code completion. As you type, the IDE intelligently suggests code snippets or names, speeding up development and reducing typos. Debugging tools. Tools that allow you to pause your application while it's running, inspect values, and step through your code line by line to find and fix problems. Project management. Ways to organize all the different files and components of your application. Your IDE is where the magic happens, where you take your ideas and translate them into a functional web application. A modern web browser, your testing client. Finally, you'll need the very thing your customers will use: a modern web browser. While your application is running on your local machine, your browser acts as the client from Chapter 1. You'll use it to send requests to your locally running ASP.NET Core application and see the responses it generates. It's your immediate feedback loop, ensuring what you build is what users will see and experience. From nothing to a running app, project creation conceptually. With your workshop set up, the first step to building an application is typically creating a new project. In ASP.NET Core, this isn't about manually crafting every file from scratch. Instead, the Net SDK provides various predefined templates. When you choose to create a new ASP.NET Core web application, it's like selecting a pre-designed blueprint for a restaurant. Do you want a blueprint for a small cafe, a simple web API, or a full-service restaurant with a dining area, a web application with a user interface? You select the appropriate template, and the tools automatically generate a basic, functional starting point for you. This starting point often includes a simple Hello World type application. When you run it using your development tools and then navigate to its address in your browser, your application will simply respond with a welcoming message. While seemingly trivial, this Hello World interaction confirms that all the pieces of your workshop are correctly connected and that the fundamental client-server communication is flowing, a crucial first test before you start building your unique culinary creations. Why a smooth setup matters. A well-configured development environment might seem like a barrier at first, but it's an investment that pays immense dividends. Just as a well-organized and equipped kitchen allows a chef to focus on cooking, a smoothly running development environment allows you, the developer, to focus on solving interesting problems and building valuable features, rather than battling with your tools. It minimizes frustration and maximizes productivity. It's worth noting that the trend in modern development is increasingly towards cloud-based environments. These setups provide your workshop entirely online within your web browser. This can simplify initial setup, as you don't need to install extensive software locally. It's like having a virtual, pre-configured kitchen that's ready to use from anywhere with an internet connection. With a conceptual understanding of the development environment in place, we're ready to peel back the layers of a typical ASP.NET Core application and understand what makes it tick. In the next chapter, we'll open up one of these project templates and peek inside its structure, much like dissecting a meal to understand its ingredients and preparation. Chapter 3. Anatomy of an application. Peering inside an ASP.NET Core project. Having intellectually, and perhaps digitally, set up our developer's workshop, it's time to examine the end product of a new project command. When you create an ASP.NET Core application from a template, you're given a structured set of files and folders. This isn't just a haphazard collection. It's a carefully organized blueprint designed for clarity, maintainability, and efficiency. Let's return to our restaurant analogy. Imagine you've decided to open a new branch of your successful restaurant. While each branch might have its unique flair, there's a standard operational manual, a kitchen layout, designated storage areas, and specific roles for the staff. An ASP.NET Core project is much the same. The project as a coherent blueprint. When you open an ASP.NET Core project in your IDE, you'll see a tree-like structure of folders and files. Each component has a specific purpose and contributes to the overall functioning of your application. While the exact files might vary slightly depending on the template you chose, e.g., a web API project versus a web application with a user interface, the underlying principles remain consistent. Let's explore the key sections of this blueprint: the operational manual, configuration files, e.g., app settings.json. Every well-run organization has an operational manual, a set of settings, preferences, and guidelines that dictate how things run. In an ASP.NET Core application, this role is largely filled by configuration files, most notably app settings.json. This file is a central place where you store settings that might change depending on where your application is running. For instance, database connection details. Where is our digital pantry located? How do we connect to it? External service addresses. If we rely on a specialized external service, like a payment processor, what's its address? Behavioral settings. Should our application log a lot of detailed information for debugging or just high-level warnings in a production environment? The beauty of app-settings.json is its flexibility. You can have different versions for different environments, e.g., app-settings.development.json, app-settings.production.json. This is like having a specific version of your operational manual for your training kitchen versus your live serving kitchen. When the application starts, it automatically loads the appropriate settings, allowing you to deploy the same application code to different environments without modification, simply by changing the configuration. The grand opening routine. Application startup logic, e.g., Program CS. When a restaurant opens its doors for the day, there's a defined set of actions that occur. Lights are turned on, equipment is powered up, staff reports in, initial preparations are made. In an ASP.NET Core application, this grand opening routine is handled by the application startup logic, primarily found in Program CS, especially in newer versions of .NET. This file is the true entry point of your application. When you launch your web application, this is the first code that runs. Its primary responsibilities include configuring services, registering all the various components and capabilities your application will use. This is like telling the restaurant staff, here are all the specialized tools, dependency injection, logging, authentication, available in our kitchen, and how they should be accessed. This lays the foundation for how different parts of your application will work together. Building the request pipeline middleware, defining the assembly line through which every incoming web request will pass. This dictates what steps, like handling errors, serving static files, or routing requests, will occur before your application logic even gets a chance to process the request. We'll dive much deeper into this in Chapter 5. Essentially, Program CS defines the overall blueprint for how your application will behave from the moment it starts until it processes its very last request. The specialized chefs, controllers and models for web APIs and MVC. Within our restaurant, different chefs specialize in different cuisines or types of dishes. Similarly, in ASP.NET Core, specific components are responsible for handling different types of incoming requests. Controllers, if an incoming web request is an order, then controllers are your specialized chefs. Each controller is designed to handle requests for a particular type of resource or feature. For example, you might have a product controller that deals with all requests related to product information, e.g., getting a list of products, adding a new product, updating product details. It receives the customer's order, figures out what needs to be done, coordinates with other parts of the system, like the database, and prepares the response. Models, while controllers handle the actions, models define the structure of the data that's being exchanged or manipulated. If a controller processes an order for a pizza, the pizza model would define what information a pizza consists of, its size, its toppings, its price. Models are like standardized forms or blueprints for information, ensuring that data is consistently formatted whether it's coming from a user, going to a database, or being sent back in a response. This separation allows for clear organization and makes it easier to manage complex applications, as each chef, controller, knows exactly what type of order they are responsible for and what information models they should be working with. The presentation and display. Views for Razor pages and MVC. Once a meal is prepared by the chefs, it needs to be presented on a plate in an appealing way for the customer. In web applications with a user interface, views serve this purpose. They are responsible for generating the actual HTML that the user's web browser will display. These files contain a blend of standard HTML, the static ingredients, and special syntax, called Razor, that allows you to embed pieces of C# code. This C# code allows the view to dynamically pull in data from your controllers, the prepared meal from the kitchen, and present it elegantly. Think of it like a beautiful plate design. The plate itself is largely static, but the specific arrangement of food items, data on it changes with each meal, guided by the instructions embedded in the Razor syntax. We will explore views, Razor, Razor pages, and MVC in more detail in Chapter 8. The project manifest, the project file, csproj. Every organized operation has a manifest, a document that lists all components, dependencies, and instructions for assembly. In an ASP.NET Core project, this is the csproj file. It's an XML file that tells the Net SDK several key things: project type. What kind of application is this, e.g., a web application, a library? References dependencies. What other existing libraries or packages does this project need to function? This is like a chef's recipe explicitly stating, you will need flour, sugar, eggs from our stock, and that special imported vanilla extract from a specific supplier. Build instructions. How should the project be compiled and packaged when it's ready for deployment? You generally don't modify this file directly by hand, your IDE manages it for you, but it's crucial for the build process and ensuring all necessary components are present. The flow. From request to response, high level. To summarize the roles, here's a highly simplified conceptual flow of an incoming web request through your ASP.NET Core application. An HTTP request arrives at your application. The application's startup logic, Program CS, has already configured the request pipeline. The request first passes through a series of middleware components defined in Program CS, which handle things like security, logging, and routing. The routing middleware consults the incoming request's URL and determines which controller or Razor page is responsible for handling it, which chef needs to take the order. The chosen controller or Razor page handler then accesses necessary models, data structures, and potentially interacts with external components, like a database, using EF Core, which we'll discuss later. Once the controller has processed the request and gathered any necessary data, it decides what to send back. This might be raw JSON data for a web API or a populated view for a user interface. The response then travels back through some of the same middleware components, allowing for any final processing, like compression or error handling, before being sent back to the customer's browser. Understanding this structure and the purpose of each main component is foundational. It allows you to navigate an ASP.NET Core project with confidence, knowing where to look for specific functionalities and how to add new ones without creating a chaotic mess. Our restaurant is now built, staffed, and has its initial operational manual. In the next chapter, we'll delve deeper into HTTP, the universal language of the web, and how our application truly talks to the outside world. Chapter 4, the language of the web, decoding HTTP and data exchange. In our ongoing restaurant analogy, we've explored the layout of the kitchen, the application structure, and the roles of its staff, controllers, models. But how do customers actually place their orders? And how does the wait staff communicate those orders to the kitchen or deliver the prepared meals back to the customer? This is where the concept of HTTP comes into play. It's the standardized, universal language that governs almost all communication on the World Wide Web. HTTP, the standardized mail system of the Internet. Imagine HTTP as the meticulously designed international postal service for information. When you want to send a letter, you don't just throw words on a piece of paper. You use a specific format, envelope, address, stamp. HTTP provides this critical structure for communication between web clients, like your browser, and web servers, our ASP.NET Core application. Every interaction over the web, from simply viewing a web page to submitting a form or streaming a video, involves an HTTP request sent from the client and an HTTP response sent back from the server. Let's break down the components of these digital messages. 1. The HTTP request, sending a letter. When your browser wants something from a web server, it sends an HTTP request. Each request contains several key pieces of information, much like parts of a physical letter. The verb, the type of letter action. This specifies the action you want the server to perform, like the type of mail service you select. The most common HTTP verbs are get, you want to retrieve information. E.g., send me the menu, show me the list of products. This is like asking for information, a query. Post, you want to send new information to the server to be created. E.g., here's my order for a new dish. Create a new user account. This is typically used for submitting forms or uploading new data. Put, you want to update existing information on the server. E.g., change my current order to update the details of this product. Delete, You want to remove information from the server. E.g., cancel this order, delete this user. Analogy: these verbs are like selecting options at the post office. Do you want to mail a letter, send a package, or formally discard something? The URL, the address. This is the precise address of the resource you are interested in on the web server. For instance, https www.example.com/products/123. https:// the protocol secure HTTP. www.example.com, the domain name, products 123. The specific path to the resource, product with ID 123. Analogy: this is the specific street address and house number you are sending your letter to. Headers, the envelope information. These are additional pieces of metadata about the request. They don't contain the main content, but important information about the content or the sender. Examples: user agent tells the server what kind of browser or device is making the request, e.g., Chrome on Windows. Content type tells the server the format of any data being sent in the body of the request, e.g., I'm sending data in JSON format. Authorization contains credentials like a digital key to identify the sender. Analogy: this is all the information written on the outside of an envelope, your return address, where it's going, priority labels, etc. Body, the letter content. For requests like POST or PUT, when you are sending data to the server, the actual data is contained within the request body. If you're submitting an online form, the form data goes here. Analogy: this is the actual message written inside the letter itself. For a GET request, the body is usually empty, as you're just asking for something. 2. The HTTP response, receiving a letter. Once the server processes your request, it sends back an HTTP response. This is the server's way of communicating the outcome of your request or providing the information you asked for. A response also has distinct parts: status code, the delivery status outcome. This is a 3-digit number that immediately tells you the general outcome of your request. 200 OK, success, everything went well. Your order was delivered perfectly. 201 created, success, a new resource was created. Your new order was successfully placed. 400 bad request, there was something wrong with your request itself. You sent incomplete or malformed instructions. 401 unauthorized, you are not authenticated. You need to log in or provide valid credentials. The restaurant requires a membership card you don't have. 403 forbidden, you are authenticated, but you don't have permission to access that resource. You're a member, but this area is only for managers. 404 not found, the resource you requested does not exist. You asked for a dish not on the menu or a table number that doesn't exist. 500 internal server error, something went wrong on the server's side. The kitchen had a major unexpected problem. Analogy: this is like the Postal Service's stamp or notification you receive, delivered. Address unknown, delivery refused. Headers, response envelope information. Similar to request headers, these provide metadata about the response. Examples: date, when the response was sent. Content type, the format of the data in the response body, e.g., I'm sending you HTML, or here's data in JSON format. Cache control, instructions for how the client should temporarily store the response. Analogy, information on the return envelope from the post office. Body, response content. This contains the actual data or content the server is sending back. For a GET request, this might be the HTML of a web page, an image, or structured data. For a POST request, it might contain confirmation of the creation or the newly created resource's details. Analogy, the actual letter or package contents that were mailed back to you. How ASP.NET Core deals with HTTP. ASP.NET Core acts as an incredibly intelligent and efficient postal worker. When an HTTP request arrives, it knows how to parse the request. It deconstructs the incoming message, understanding its verb, URL, headers, and body. Route the request. It then efficiently directs the request to the correct part of your application, the right chef or controller method based on the URL and verb. Process and generate response. Once your application's logic has completed its task, ASP.NET Core helps in constructing the HTTP response, setting the correct status code, adding necessary headers, and formatting the response body correctly. Data exchange formats, speaking a common dialect. While HTTP is the grammar and syntax of web communication, the content of the message can be structured in different formats. The most prevalent language for data exchange in modern web applications and APIs is JSON. JSON, JavaScript Object Notation, the universal data recipe. Imagine you're trying to explain a complex recipe, like a gourmet stir-fry, over the phone to a friend. You wouldn't just ramble, you'd likely use an organized list of ingredients and steps. JSON is exactly that, a human-readable, yet machine-parsable, way to represent structured data. It uses simple key-value pairs, much like defining characteristics. Name, spaghetti carbonara, the dish's name is spaghetti carbonara. Servings, 4, it serves 4 people. Ingredients, pasta, eggs, cheese, it has a list of ingredients. JSON is widely adopted because it's lightweight and easy for both humans to read and computers to process efficiently. When you request data from a web API, chances are you'll receive it in JSON format. When you send data to an API, e.g., submitting a form, you'll often send it as JSON in the request body. Contrast with XML, extensible markup language. Historically, XML was also popular for data exchange, but JSON has gained prominence due to its simpler structure and less verbose nature, especially for web-based services. Think of XML as using very rigid, descriptive labels for everything, like dish name spaghetti carbonara name dish, while JSON is more direct, like name spaghetti carbonara. Res-TFL principles, standardizing the conversation. When web APIs are built in a res-TFL manner, it means they adhere to a set of principles that leverage HTTP verbs and URLs in a consistent and predictable way to interact with resources. Resources. In a res-TFL API, everything is treated as a resource. A product, a user, an order, these are all conceptual resources that can be identified by a unique URL. For example, products might represent the collection of all products, and products 123 would represent a specific product with the ID 123. Applying HTTP verbs to resources, get products, retrieve a list of all products. Get products 123, retrieve details for product ID 123. Post products, create a new product, sending the product data in the request body. PUT products 123, update all details for product ID 123, sending the updated product data. Delete products 123, remove product ID 123. By following these principles, different systems across the internet can understand how to talk to your ASP.NET Core applications, APIs, without needing highly specialized, custom instructions, making integration much smoother. It's like having every restaurant agree on a universal language for ordering food, making it easy for anyone to place an order, regardless of where they are from. Understanding HTTP and data formats like JSON is fundamental because they are the very fabric of web communication. Your ASP.NET Core application is designed to speak this language fluently. In the next chapter, we'll see how ASP.NET Core effectively processes these incoming requests through its request pipeline, a sophisticated assembly line that handles every byte of an incoming message. Chapter 5. The Request Assembly Line, Understanding Middleware and the Request Pipeline. In the previous chapter, we explored HTTP, the language of the web, and how requests and responses are structured. Now, let's step inside our ASP.NET Core application and see how it actually processes an incoming HTTP request. This is where the concept of the request pipeline and middleware becomes crucial. Imagine an intricate assembly line in a factory. A raw product enters at one end, and it passes through a series of specialized stations. Each station performs a specific task, adding a component, checking quality, packaging, and then passes the product to the next station. By the time it reaches the end, it's a finished product ready for shipment. The ASP.NET Core request pipeline is exactly like this assembly line. Every incoming HTTP request, the raw product, enters this pipeline, and it moves through a series of components called middleware, the specialized stations. Each piece of middleware performs a specific function on the request before either passing it along to the next middleware or, in some cases, directly generating a response and sending it back. What is middleware? Middleware is a small, modular component that sits in the request pipeline and can inspect or modify the incoming request. As a request, our product, enters its station, the middleware can look at it, read its headers, or even change parts of it. Perform an action based on the request. It might log data, check for security credentials, or redirect the request to a different address. Short-circuit the pipeline. Sometimes, a piece of middleware handles the request entirely and generates a response immediately, preventing the request from proceeding further down the line. This is like a quality control station that identifies a fatal flaw and sends the product back instantly, without it needing to go through the entire assembly line. Inspect or modify the outgoing response. After the request has been processed by subsequent middleware or the main application logic, the response travels backwards through some of the same middleware components, allowing them to perform final tasks, like adding response headers or compressing data before the response is sent back to the client. How the pipeline works, a journey through stations. When an HTTP request arrives at your ASP.NET Core application, it first hits the very first piece of middleware configured in the pipeline. This middleware performs its job and then explicitly calls the next middleware in the sequence. This continues until the request reaches a middleware component or your main application logic, like a controller, that decides it can handle the request completely. At that point, a response is generated. This response then travels back up the pipeline, passing through the middleware components it previously traversed, but in reverse order. This gives each middleware a chance to do any post-processing before the response leaves the application. This two-way flow is powerful, allowing middleware to act both before and after the core application logic executes. Common examples of middleware in your application. Your ASP.NET Core application comes equipped with common pieces of middleware that handle frequently needed tasks. Exception handler middleware, the safety net. Purpose catches any unhandled errors or exceptions that occur further down the pipeline. Analogy. This is the emergency brake system on our assembly line. If any station downstream malfunctions and creates a critical error, the exception handler catches it, prevents the assembly line from crashing completely, and instead produces a graceful error message for the customer. It prevents sensitive internal information from being leaked in public error messages. HTTPS redirection middleware, the security guard. Purpose ensures that all incoming requests use the secure HTTPS protocol. If an insecure HTTP request comes in, it automatically redirects it to the secure version. Analogy. A security checkpoint that insists all visitors use the secure main entrance. If someone tries to use a less secure side door, they are politely but firmly redirected to the main one. Static files middleware, the resource manager. Purpose serves static files directly from your application's folders, like HTML files, CSS style sheets, images, or JavaScript files. Analogy. A dedicated section of the factory that fulfills requests for standardized components, like screws, nuts, or pre-printed labels, without needing to involve the complex main assembly line. If a request is for an image, this middleware finds it and serves it directly, short-circuiting the rest of the pipeline. Routing middleware, the traffic controller. Purpose examines the incoming request's URL and determines which specific part of your application, e.g., a particular web API endpoint or a Razor page, should handle that request. Analogy. The central traffic control tower that directs incoming planes, requests to the correct terminal gates, specific controllers or pages, based on their flight number, URL, and type HTTP verb. Authentication middleware, the identity verifier. Purpose determines who the incoming request is from. It checks credentials, like login cookies or security tokens, to establish the user's identity. Analogy. The security guard at the building entrance checking everyone's ID badge. They don't decide what you can do, just who you are. Authorization middleware, the permission checker. Purpose. After a user's identity has been established, This middleware determines what that user is allowed to do or which resources they can access. Analogy. Once you're inside the building, this is the floor manager checking your ID badge against a list of authorized areas. You might be an employee, but you may not be authorized to enter the executive offices. Configuring the pipeline, the startup blueprint. The order in which you configure middleware in your application's startup logic, recall Program CS from Chapter 3, is absolutely crucial. Because middleware components process requests sequentially, the order often matters. For instance, typically you'd want to handle errors before anything else, ensure secure connections, then define who the user is, then check what they're allowed to do, and only then route the request to the specific application logic. The powerful concept of a modular, configurable pipeline means that you can easily add, remove, or reorder functionalities that apply to every incoming request without cluttering your core application logic. It promotes a clean separation of concerns, making your application easier to build, maintain, and scale. Understanding this assembly line of middleware provides deep insight into how ASP.NET Core efficiently processes every interaction. In the next chapter, we'll explore another cornerstone of modern ASP.NET Core development: dependency injection, a technique that drastically improves the flexibility and testability of your application's components. Chapter 6, Building with Flexibility, the Magic of Dependency Injection. In the preceding chapter, we looked at how ASP.NET Core processes requests with its powerful middleware pipeline. Now, let's zoom in on a fundamental design principle that deeply impacts how individual components within your application are built and interact. Dependency injection, DI. This concept is so central to modern ASP.NET Core that it needs its own dedicated discussion, even without writing a line of code. The fragile machine problem. Imagine you're building a complex machine, perhaps a sophisticated coffee maker. If you hardwire every single component directly to every other component, the water pump is soldered directly to the heater, which is directly bolted to the coffee grinder. What happens if you want to upgrade the water pump? You'd have to cut wires, unsolder connections, replace the part, and then resolder everything. If you decide to use a different brand of coffee grinder, you might have to redesign large parts of your machine. This tight coupling makes the machine fragile, difficult to repair, expensive to upgrade, and nearly impossible to test individual parts without running the entire device. This fragile machine problem is common in software development when components are tightly coupled. If one part of your code directly creates and manages all the other pieces it needs to work, it becomes rigid and inflexible. Dependency injection, the smart assembler. Dependency injection is a design pattern that solves this problem. It's an elegant solution where, instead of a component creating or finding its own dependencies, the other pieces of code or services it needs to function, those dependencies are provided to it from an external source. Let's revisit our machine analogy. Instead of hardwired components, imagine our coffee maker uses standardized ports and connectors. The water pump connects via port A, the heater via port B, and the grinder via port C. Now, when you want to upgrade the water pump, you simply plug in a new one, as long as it adheres to the port as standard. In the world of software, a dependency is simply something that a class or component needs to do its job. For example, a product catalog component might depend on a database service to retrieve product information, or an order processor component might depend on an email sender to send confirmation emails. With dependency injection, the core idea is, don't build your dependencies yourself. Don't go looking for your dependencies yourself. Let someone else provide your dependencies to you. Think of a modern car assembly line. A worker on the line doesn't build the engine from raw materials, nor do they go searching for an engine out in the factory yard. Instead, when a car chassis arrives at their station, the precise engine needed is already there, ready to be installed. The assembly line itself, an external system, is injecting the engine into the car. Benefits of dependency injection. This seemingly simple shift in responsibility offers profound benefits. Loose coupling. This is the primary advantage. Components become independent, relying only on a contract, an interface in programming terms, which defines what a component does rather than how it does it, for their dependencies. This means you can swap out one implementation of a service, e.g., a SQL database service, for another, e.g., a cloud database service, without changing the code that uses that service, as long as both implement the same contract. This is like swapping a new water pump, different brand, same port compatibility, into our coffee maker. Testability. This is invaluable for quality assurance. When you're testing an order processor that sends emails, you don't necessarily want to send real emails during a test. With DI, you can inject a fake email sender, a mock or stub, that simulates sending emails without actually doing so. This allows you to isolate and test just the order processor's logic, ensuring it works correctly without side effects or reliance on external systems. Maintainability. Code becomes easier to understand and manage. Each component has a clear responsibility and doesn't worry about how its dependencies are created or managed. This reduces complexity and makes debugging simpler. Reusability. Components that are loosely coupled can be reused in different contexts or even in different applications, as their dependencies can be tailored to the specific environment. How dependency injection works in ASP.NET Core. ASP.NET Core has a built-in, first-class dependency injection container, also known as an IOC, inversion of control container. This container is the smart assembler for your application. The process conceptually involves two main steps: registration. In your application's startup logic, recall Program CS from Chapter 3, you register the services or components you want the DI container to manage. This is like telling the assembly line, when someone asks for an iPayment processor, here's how to provide one, always use the Stripe payment processor. You define the interface, what service, and the implementation, how it's provided. During registration, you also specify the lifetime of the service. Singleton. The DI container creates only one instance of the service for the entire application's lifetime and reuses it for every request, like a shared power tool for the whole factory. Scoped. A new instance of the service is created once per HTTP request and reused within that single request, like a fresh pair of gloves provided for each new task. Transient. A brand new instance of the service is created every single time it is requested, like a new disposable tool for every small step. The choice of lifetime depends on the nature of the service and its state. Resolution injection. When ASP.NET Core needs to create an instance of a component, like a controller that needs a product catalog, it inspects that component's requirements, often passed through its constructor. The DI container then automatically looks up the registered services and provides the correct instances. This is frictionless background work. You just specify what you need, and the container delivers. So, for example, if your product's controller needs a iProduct repository, an interface for data access, you simply declare that requirement in the controller's blueprint. When ASP.NET Core creates an instance of product's controller to handle an incoming request, its DI container sees this need, finds the product repository implementation you registered, creates it, if necessary according to its lifetime, and hands it over to the controller. The controller doesn't care how it got the repository, only that it has one that fulfills the iProduct repository contract. A foundational stone. Dependency injection is not just a fancy term. It's a foundational architectural philosophy that underpins much of modern ASP.NET Core development. It empowers developers to build applications that are more adaptive, easier to test, and more manageable as they grow in complexity. It's an essential pattern for ensuring that your application remains flexible and robust as your cooking techniques evolve. With a solid understanding of how components are responsibly assembled and connected, we're now ready to delve into specific types of web applications you can build. In the next chapter, we'll focus on crafting digital services, building web APIs with ASP.NET Core. Chapter 7, Crafting Digital Services, building web APIs with ASP.NET Core. In our journey so far, we've dissected the anatomy of a web application, understood the fundamental language of the web, HTTP, seen how requests travel through the pipeline, and appreciated the flexibility that dependency injection offers. Now it's time to talk about building something concrete, web APIs. You interact with web APIs every single day, often without realizing it. When your smartphone's weather app fetches the latest forecast, when you share a photo on social media, or when an online travel site shows you flight prices from various airlines. Behind the scenes, these applications are talking to web APIs. What is a web API? The digital waiter analogy. Recall our restaurant analogy. Sometimes, a customer isn't a human sitting at a table desiring a full, plated meal. Sometimes, the customer is another digital system. Perhaps a mobile app, another website, or even a smart device that just needs raw data or wants to perform a specific action without any visual presentation. A web API, application programming interface, is like a highly specialized digital waiter. Its job is not to serve beautifully presented web pages to humans. Instead, it takes structured requests from other applications, in formats like JSON, performs actions or retrieves data from the backend systems, and then sends back structured responses, also often in JSON, that those applications can easily understand and process programmatically. It's literally an interface that allows one computer program to talk to another computer program over the internet using the familiar HTTP protocol. Why are web APIs so crucial? Data sharing. APIs provide a standardized way to expose and share data. A single API can feed data to multiple different applications, your website, your mobile app, or partner systems. Cross-platform compatibility. Because APIs communicate using common web standards, HTTP and JSON, they are inherently platform agnostic. A single ASP.NET Core Web API can seamlessly serve data to an iPhone app written in Swift, an Android app written in Kotlin, a JavaScript-based front-end framework, or even a desktop application. Separation of concerns. APIs enforce a clean separation between the backend, where data is stored and business logic resides, and the front end, the user interface. This allows development teams to work independently, and either part can be updated or even replaced without necessarily affecting the other. Modularity and scalability. Large applications can be broken down into smaller, independent services, or microservices, each exposing its own API. This makes systems easier to develop, maintain, and scale. An API that receives flight bookings might be scaled up independently of the API that manages user profiles. For instance, building web APIs with ASP.NET Core. The REST-TFL approach. ASP.NET Core is an excellent choice for building web APIs, and it highly promotes the REST-TFL approach we touched on in Chapter 4. This means structuring your API using HTTP verbs and URLs to represent interactions with resources in a consistent, intuitive way, much like a well-organized menu with clear sections and dish names. Let's illustrate with an example, managing hypothetical products in an online store. API controllers, the digital service chefs. In ASP.NET Core, the primary component for building web APIs is the API controller. These are specialized chefs, from our analogy in Chapter 3, dedicated to serving digital requests. Each method within an API controller typically responds to a specific HTTP verb and path. Imagine a products controller with methods like these, conceptually. Get all products. When an incoming request is a get to /API/products, this method handles it. It would likely go to a database. Using EF-Core, discussed in Chapter 9, retrieve a list of all products, convert them into a structured format, like a list of JSON product objects, and send them back as the HTTP response body, along with a 200 OK status code. Get product by ID. A GET request to /API/products/ID, e.g., /API/products/123 would trigger a method that takes the ID from the URL, finds that specific product in the database, and returns its details as JSON. If the product isn't found, it returns a 404 not found status. Create new product. A post request to /API/products would activate a method designed to accept new product data. The incoming product data, usually JSON in the request body, is automatically parsed by ASP.NET Core, converted into a C# product model, validated, saved to the database, and then a 201 created status with the newly created product's details including its new ID, is sent back. Update product. A PUT request to /API/product/ID would trigger a method that takes the ID and the updated product data. It would find the existing product, update its details in the database, and return a 200 OK or 204 no content status. Delete product. A delete request to /API/product/ID would trigger a method to remove the specified product from the database, returning a 204 no content status upon success. Input and output, speaking JSON fluently. One of the significant advantages of ASP.NET Core for APIs is its excellent handling of JSON. Receiving JSON. When your API receives an incoming post or put request with a JSON body, ASP.NET Core is incredibly smart. It can automatically deserialize, convert that JSON data into the appropriate C-hash object, your product model, for instance, making it easy for your controller methods to work with structured data. This saves you from writing tedious parsing code. Sending JSON. Similarly, when your API controller methods return a C-hash object, ASP.NET Core automatically serializes, converts that object into a JSON string, and sends it back in the HTTP response body. This ensures that the consuming application receives data in a universally understandable format. Statelessness, the server forgetting the past. A core principle of REST-TFL APIs is statelessness. This means that each request from a client to an API server contains all the information needed to understand the request. The server doesn't remember past requests from that client or rely on previous interactions for processing the current one. Analogy: every time you send a letter through the postal service, that letter must contain all the information needed to deliver it. The postal worker doesn't remember your previous letters or use information from them to deliver the current one. Each interaction is self-contained. This makes APIs highly scalable because any server can handle any request at any time without needing to maintain specific session or connection information for each client. Status codes. The language of success and failure. We discussed HTTP status codes in Chapter 4. For APIs, these codes are not just informative, they are critical. Consuming applications rely heavily on these numerical codes to understand the outcome of their requests. A 2XX status, like 200 OK, 201 created, 204 no content, indicates success. A 4XX status, like 400 bad request, 401 unauthorized, 403 forbidden, 404 not found, indicates a client-side error. The client sent something wrong or is not allowed to do something. A 5XX status, like 500 internal server error, indicates a server-side problem. Correctly returning these status codes is paramount for building robust and reliable APIs, as they guide the consuming application on how to proceed. Building web APIs is a core strength of ASP.NET Core. It provides a robust, high-performance, and developer-friendly environment for creating the digital services that power today's interconnected applications. In the next chapter, we'll shift our focus from digital clients to human users, exploring how ASP.NET Core helps us build the user interfaces that people see and interact with, specifically through the concepts of Razor Pages and MVC. Chapter 8, The User Interface Canvas, Conceptualizing Razor Pages and MVC. We've fully explored how ASP.NET Core excels at building web APIs, the digital services that other applications consume. But what if your customer is a human sitting in front of a web browser, expecting a visually rich and interactive experience? This is where ASP.NET Core provides powerful tools for building web user interfaces, UIs, primarily through two popular architectural approaches: Razor Pages and Model View Controller, MVC. Both Razor Pages and MVC rely on a special templating language called Razor, which allows you to seamlessly blend C-hash code with HTML to generate dynamic web content. Razor syntax, blending logic and markup. Imagine you have a template for a personalized greeting card. Most of the card is fixed, the design, the standard text, but there are specific parts where you can insert custom messages, display someone's name, or even repeat a section for each item in a list. Razor syntax is like that. It allows you to write standard HTML, but then within that HTML, use special markers, starting with the @ symbol, to embed C# code. This code executes on the server before the page is sent to the user's browser, generating dynamic content. For instance, you could have a line like h1 welcome at model.username/h1. The at model.username part tells the server to fetch the user's name from a data structure and insert it directly into the HTML heading. Or ul at forh, var item in model.items. Li at item.name li/ul would instruct the server to loop through a list of items and generate a list item li for each one. This blending of C# and HTML in a highly readable way is fundamental to both Razor Pages and MVC. 1. Razor Pages, the page-centric approach. Think of a single recipe card for a particular dish. On one side, you have the ingredients and cooking instructions. On the other, you have a beautiful picture of the final plated meal and perhaps some serving suggestions. Everything related to that one dish is self-contained on its card. Razor Pages operates on this principle. It's a page-focused architectural pattern within ASP.NET Core. For each web page you want to create, e.g., an About Us page, a contact form, or a product details page, you typically have two files that work together. The CS.html file, the presentation view. This is your HTML content mixed with Razor syntax. It defines how the page looks and where dynamic content should be inserted. This is the picture of the plated meal and serving suggestions. The CS.html/CS file, the code behind logic. This is a C# file containing the code that handles all the logic for that specific page. It processes incoming requests, retrieves data, handles form submissions, and prepares any data needed by the CS.html file. This is the ingredients and cooking instructions. How it works conceptually. When a browser requests a specific URL, ASP.NET Core's routing system, recall our traffic controller middleware, knows to map that URL directly to a Razor page. The logic in the CS.html/CS file executes first, preparing the necessary data. Then, that data is passed to the CS.html file, which uses the Razor syntax to dynamically generate the final HTML. This HTML is then sent to the browser. Advantages of Razor Pages: simplicity and cohesion. Because the HTML markup and the C# logic for a single page are kept together or very close, it's often easier to understand and manage smaller, self-contained features. Ideal for page-oriented applications. Perfect for building websites with distinct, individual pages or form-heavy applications. Easier to learn, often considered more approachable for developers new to ASP.NET Core or web development, as it directly relates a file to a URL. 2. Model View Controller, MVC, the component-centric approach. If Razor Pages is about individual recipe cards, Model View Controller, MVC, is like a highly organized, professional kitchen with specialized teams for each part of the cooking process. It's an architectural pattern that separates concerns into 3 distinct roles, each focusing on a specific responsibility. Model, the ingredients, data structure, and business rules. The model represents the data of your application and any business rules that apply to that data. It's not just raw data, but also the logic for how that data behaves. Analogy. This is the pantry and the head chef's recipe database. It contains all the ingredients, data like product or customer information, and the associated rules, e.g., a product's price must be positive, or how to calculate the total for an order. The model is independent of how the data is displayed or how user input is received. View, the plated meal presentation. The view is responsible solely for the presentation of the user interface. It's the HTML generated using Razor syntax that the user actually sees in their browser. Analogy. This is the beautifully arranged plate containing the finished meal data from the model provided by the controller. The view's job is simply to display. It doesn't contain any complex business logic. Controller, the coordinator chef. The controller acts as the intermediary, orchestrating the flow between the model and the view. It receives user input, get requests for pages, post requests from forms, interprets that input, interacts with the relevant model to retrieve or modify data, and then selects the appropriate view to display the result to the user. Analogy: this is the expediter chef in the kitchen. They take the customer's order, tell the ingredient team, model, what to prepare, then tell the presentation team, view, how to arrange it, and finally send it out to the customer. They don't cook directly, they manage the process. How it works conceptually: a user makes an HTTP request to a specific URL, e.g., www.example.com/products/details/123. ASP.NET Core's routing maps this URL to a method within a specific controller, e.g., the product's controller's details method. The controller method executes. It might call a service to fetch product data from the database, the model. Once the controller has the data, it selects a view, e.g., the details CSHTML view, and passes the collected product data to it. The view, using Razor, renders the data into HTML. The final HTML is sent back to the user's browser. Advantages of MVC: clear separation of concerns. The distinct roles of model, view, and controller make it incredibly easy to manage large, complex applications, as each part has a single, well-defined responsibility. Testability: since components are separated, you can test the controller's logic independently of the view and the model's logic independently of both. Team collaboration: different team members can work on different layers, e.g., one person on the model backend logic, another on the view layout, without interfering with each other's work as much. Choosing between Razor Pages and MVC. ASP.NET Core supports both Razor Pages and MVC, allowing you to choose the best fit for your project. Use Razor Pages when you are building a simpler, page-oriented application or a site that is primarily static content with embedded forms. You prefer having the UI and its specific logic closely together. You are new to web development and want a simpler learning curve. Use MVC when you are building large, complex applications where clear separation of concerns at a broader level is highly beneficial. You need fine-grained control over routing or want to implement complex architectural patterns. Your team is already familiar with the MVC pattern. You anticipate extensive unit testing of your UI logic controllers. It's also important to note that you can even use both in the same ASP.NET Core application. Perhaps leveraging Razor Pages for simpler parts of your site and MVC for more complex, component-driven sections. No matter which you choose, ASP.NET Core, powered by the flexible Razor syntax, provides a robust and efficient way to build engaging user interfaces. Now that we've seen how to present data to the user, the natural next step is to understand how your application gets and manages that data consistently. In the next chapter, we'll delve into Entity Framework Core, ASP.NET Core's powerful tool for interacting with databases. Chapter 9, the Data Repository, Managing Information with Entity Framework Core. So far, we've explored building the shell of our web application, its structure, its communication language, its logical flow, and its user interface. But what good is a restaurant without food or a library without books? For most dynamic web applications, the true value lies in the data they manage. Websites like online stores, social media platforms, or banking applications all need to persistently store, retrieve, and manipulate vast amounts of information. This is where databases come in. They are organized storage systems for digital information, much like a meticulously organized filing cabinet or a vast warehouse redesigned for digital goods. But how does your ASP.NET Core application, written in C#, seamlessly talk to a database that typically understands its own query language, often SQL, structured query language? This is the problem that Entity Framework Core, EF Core, elegantly solves. The problem EF Core solves: the language translator analogy. Imagine you, speaking English, your C# application, need to retrieve and organize physical records stored in a vast archive where everything is indexed and retrieved using a different language and specific syntax. SQL, the language of databases. You need to learn that language, formulate precise requests, and then translate the results back into English to make sense of them. This would be incredibly tedious and repetitive. Entity Framework Core acts as your personal, highly intelligent translator and archivist. It understands both your English, C# objects, and the archive's SQL, database tables. It bridges the gap, allowing you to ask for data using your familiar C# language, and it handles all the complex translation behind the scenes. This fundamental concept is known as Object Relational Mapping, ORM. What is Object Relational Mapping, ORM? Objects. In your C# code, you work with objects. For example, you might have a product object with properties like id, name, price, and description. Relational database. The data for these products is stored in a relational database, typically in tables. A products table would have columns like id, name, price, and description. Each row in the table would represent a single product. An ORM system essentially maps these C# objects to database tables. It means you can interact with your database using C# objects and familiar C# syntax, rather than writing raw SQL queries. EF Core then takes your C# instructions, translates them into the appropriate SQL queries, sends them to the database, receives the results, and converts them back into C# objects for your application to work with. Key concepts in EF Core. Models, the data blueprints. These are simple C# classes that represent the tables in your database. For instance, you would define a product class in C# with properties matching the columns in your products table. EF Core uses these blueprints to understand the structure of your data and how it relates to the database. DB Context, the Database Session Manager. This is the central class in EF Core, acting as the concierge for your database interactions. Your DB Context class represents a session with your database. You define collections of your models, e.g., DB set product products, within your DB context to tell EF Core which sets of data your application needs to work with. The DB context is responsible for querying, translating your C# queries into SQL, tracking changes, keeping track of any changes you make to the objects you've retrieved, e.g., changing a product's name, saving changes, persisting those changes back to the database, queries asking the database with LINQ. Instead of writing SQL, EF Core allows you to use LINQ, Language Integrated Query. LINQ is a powerful feature of C# that lets you write queries using C# syntax, which then get translated into SQL by EF Core. Conceptual example. Instead of writing, select from products where price 50 order by name ASC, you would conceptually instruct your DB context. Give me all the products where the price is greater than 50, and then sort them by their name in ascending order. This means you reap the benefits of type safety. Your IDE catches errors if you try to query a property that doesn't exist, and don't have to embed string-based SQL queries directly into your code, making it less error-prone and more readable. Basic data operations, conceptual. EF Core simplifies the common database operations. Adding data. To save a new product, you conceptually create a new product object in C#, add it to the products collection on your DB context, and then tell the DB context to save changes. EF Core handles generating the insert SQL statement. Retrieving data. To get a product, you query your products collection on the DB context. EF Core translates this into a select SQL statement. Updating data. To update a product, you retrieve it using the DB context, modify its properties in C, and then call save changes. EF Core detects the changes and generates the update SQL statement. Deleting data. To delete a product, you retrieve it or create a reference to it, tell the DB context to remove it from the products collection, and call save changes. EF Core generates the delete SQL statement. The critical point is the save changes method. When you make changes to objects attached to the DB context, adding, modifying, deleting, those changes are only reflected in your application's memory. They are not written to the actual database until you explicitly call save changes. This allows you to group multiple operations into a single transaction, ensuring data consistency. Migrations, database evolution. Databases are rarely static. As your application evolves, you often need to change your database schema, add a new column, change a data type, or create a new table. EF Core migrations provide an incredibly powerful way to manage these changes. Concept. Instead of manually writing SQL scripts to alter your database, you modify your C# model classes, e.g., add a new property to your product class. Then, you conceptually tell EF-Core to create a new migration. EF-Core compares your changed C# models to the current state of your database and automatically generates a C# class that acts as a set of instructions, often called migration scripts, to update your database schema accordingly. Benefit: this allows your database schema to evolve in sync with your application code, providing a clear history of changes and preventing issues when deploying updates. It's like having an automated tool that takes your updated building blueprint and generates precise instructions for how to change the physical building without tearing it down. The power and flexibility of EF-Core. EF-Core provides developers with immense power and flexibility. Reduced boilerplate code. You don't need to write repetitive SQL or data access code. Type safety. C# compiler checks ensure your queries are valid, catching errors early. Database agnostic. While primarily used with relational databases like SQL Server, PostgreSQL, MySQL, SQLite, EF-Core also has providers for other database types, allowing you to switch databases with minimal code changes. Productivity. It significantly speeds up data access development, letting you focus on your application's unique business logic. Integrating EF-Core into your ASP.NET Core application typically involves registering your DB context with the Dependency Injection container, as discussed in Chapter 6. This makes your DB context available to your controllers and other services, allowing them to effortlessly interact with your database without worrying about connection management or translation. With EF-Core, your ASP.NET Core application gains its long-term memory, enabling it to store, retrieve, and manage the valuable information that truly brings it to life. However, simply having data isn't enough. We also need to protect it and ensure only authorized users access it. In the next chapter, we'll delve into the critical topics of authentication and authorization. Chapter 10, Digital Guardians. Authentication and authorization in ASP.NET Core. As we build increasingly sophisticated web applications, the need for robust security becomes paramount. We've established how our ASP.NET Core application processes requests, manages data with EF-Core, and presents user interfaces. But what prevents just anyone from accessing sensitive customer data, making unauthorized purchases, or changing critical settings? This is where the crucial concepts of authentication and authorization come into play. Let's use an analogy of a secure building to understand these two distinct, yet interconnected, processes. 1. Authentication. Who are you entering the building? Authentication is the process of verifying a user's asserted identity. It's about answering the question, is this user who they claim to be? Analogy. When you arrive at a secure building, the first thing you do is prove your identity to the security guard at the entrance. You might show your driver's license, swipe an ID card, or use your fingerprint. The guard doesn't care what you're going to do inside. They only care if you are a valid person allowed to enter the premises. In a web application, authentication typically involves credentials. A user provides proof of identity, most commonly a username and password. This could also be a fingerprint scan, biometrics, a one-time code sent to their phone, multi-factor authentication, or logging in through a third-party service like Google or Facebook. Verification. The application checks these provided credentials against a stored record, e.g., in a database managed by EF-Core. This record usually doesn't store the raw password, but a secure representation of it, a hashed version to protect against data breaches. Identity establishment. If the credentials are valid, the application establishes a digital identity for that user. This identity carries various claims or facts about the user, e.g., their user ID, email address, the time they logged in. Session management. For web applications, once authenticated, the user typically doesn't have to log in for every single request. Instead, the server issues a small, encrypted piece of information, often stored in a browser, cookie, or as a bearer token, that serves as a temporary ID badge. This badge is sent with every subsequent request for a defined period, proving the user's identity to the server without re-entering credentials. ASP.NET Core Identity. For comprehensive user management, ASP.NET Core provides ASP.NET Core Identity. This is a powerful, ready-to-use framework that handles user registration, login, password management, roles, external logins, like Google, Facebook, and multi-factor authentication. It provides the secure identity verification desk for your application, saving you from having to build all these complex features from scratch. 2. Authorization. What can you do? Accessing specific rooms. Once a user's identity has been successfully authenticated, authorization determines what actions that user is allowed to perform and what resources they can access. It answers the question, given who this user is, what are they permitted to do? Analogy, you've shown your ID and entered the secure building. Now, you try to open a door to a restricted area, say, the server room or the executive boardroom. The authorization system checks your ID badge, your established identity, against a list of permissions. If your badge indicates you're an employee but not an IT administrator or executive, you'll be blocked. Your identity is confirmed, but your access is denied. ASP.NET Core offers flexible ways to manage authorization. Role-based authorization. This is a common approach where users are assigned roles, e.g., administrator, editor, buyer, guest. You then specify that certain parts of your application, a page, an API endpoint, a specific function, require particular roles. Conceptual example. An API endpoint for deleting products might only be accessible to users in the administrator role. A page for editing articles might only be accessible to editor or administrator roles. Claim-based authorization. This is a more granular and powerful approach. Instead of just roles, users are given claims. A claim is simply a piece of information or a fact about the user. Examples of claims: email verified, true, department, sales, has permission, manage products, age. 35. You then define policies that require specific claims. For instance, a big spender policy might require a claim like total purchase list year, $10,000. A discount page might only be accessible to users who satisfy this policy. This is like a personalized access card that might grant you access to specific floors, even if you're not formally an executive, simply because you hold certain necessary clearances. Policy-based authorization. ASP.NET Core's rich model allows you to define complex authorization policies that combine role checks, claim checks, or even evaluate custom logic. This system lives within the request pipeline, recall authorization middleware from Chapter 5, and rigorously enforces rules before your application's business logic is executed. How authentication and authorization work together, conceptual flow. An HTTP request arrives at your ASP.NET Core application. The authentication middleware, from Chapter 5, intercepts the request. It checks for proof of identity, e.g., the temporary ID badge from a login cookie. If the identity is valid, the user is authenticated, and a digital identity, with associated claims roles, is established for the duration of that request. If not, the user might be redirected to a login page or given an unauthorized response. Next, the authorization middleware steps in. It inspects the request destination's, e.g., products controller's delete method, and checks any authorization rules attached to it, e.g., requires administrator role. It then examines the authenticated user's digital identity to see if they possess the required roles or claims. If the user is authorized, the request proceeds to your application's business logic, e.g., the products controller method will execute. If not, the request is immediately short-circuited by the middleware, returning a forbidden 403 status or redirecting to an access-denied page without ever touching your sensitive business logic. Security is a journey, not a destination. Authentication and authorization are critical layers of defense, but they are just part of overall application security. Beyond these concepts, applications must also consider input validation, ensuring that user-provided data is safe and what the application expects, preventing malicious injection attempts. Data protection, securely storing sensitive data, like passwords, credit card numbers, using encryption and hashing. Secure communication, always using HTTPS to encrypt data in transit over the network. Vulnerability scanning, regularly checking for common web vulnerabilities, e.g., SQL injection, cross-site scripting. ASP.NET Core provides robust, built-in features for both authentication and authorization, significantly simplifying the complex task of securing your applications. This allows developers to focus on defining their business rules for access, rather than building the underlying security mechanisms from scratch. With our application now securely handling who can access what, the next crucial step is to ensure that it not only functions correctly, but also performs efficiently. In the next chapter, we'll shift our focus to exploring testing and performance concepts. Chapter 11, Ensuring Quality and Speed, exploring testing and performance concepts. So far, we've covered the fundamental building blocks of an ASP.NET Core application: its structure, communication, data management, and security. But assembling a masterpiece, whether a culinary delight or a software application, doesn't end with getting all the ingredients in place. It also requires rigorous quality control and efficiency checks to ensure it runs smoothly, reliably, and delivers the best possible experience to its users. This brings us to two critical aspects of software development: testing and performance optimization. Why test your application? The quality assurance check. Imagine launching a new signature dish at your restaurant without ever having tasted it, or serving a car without ensuring its brakes work. The results would be disastrous. Software applications are no different. Testing is the process of evaluating a system or its components with the intent to find whether it satisfies the specified requirements or to identify defects. The benefits of systematic testing are immense. Bug detection. Catching errors early before they reach your users saves significant time and cost. Reliability. Gives confidence that the application works as expected under various conditions. Maintainability. Ensures that new features or changes don't unintentionally break existing functionality. User satisfaction. A bug-free, reliable application leads to happier users. In the world of ASP.NET Core, testing is woven into the development process. Let's look at the main types of testing. Unit testing, the individual ingredient test. Concept. Unit tests focus on the smallest, isolated parts of your code, often a single function or a method within a class. The goal is to verify that each unit performs its specific task correctly. Analogy. If you're building a car, a unit test would be like individually testing a single spark plug to ensure it fires correctly under specific conditions. It doesn't test the whole engine, just that one component in isolation. How it works conceptually. You write separate, small pieces of code test methods that call a specific method in your application. These test methods provide specific inputs and then assert that the method produces the expected output or behaves in the expected way. Role of dependency injection. This is where the power of dependency injection from Chapter 6 shines. If a method you're unit testing relies on a database or an external service, you inject a mock or fake version of that dependency. This allows you to test your method in complete isolation without waiting for database calls or relying on external systems. Integration testing, testing the subassemblies. Concept. Integration tests verify that different components or layers of your application work correctly together. This often involves testing the flow of data through multiple parts of your system. Analogy. Continuing with the car analogy, an integration test would be like testing how the engine, transmission, and wheels connect and work together as a single subassembly. You're not testing the whole car on the road yet, but you're ensuring the critical parts interact correctly. How it works, conceptually. In ASP.NET Core, you can write integration tests that run your actual application in a test host. You can simulate HTTP requests being sent to your API endpoints or web pages, and then verify that the response contains the expected data, status codes, or content. These tests might even use a real, but usually test-specific database to ensure data persistence works correctly. Functional end-to-end testing, briefly, the full road test. Concept. These tests simulate real user interaction with the entire application, from clicking buttons in the browser to verifying database updates. Analogy. taking the fully assembled car for a complete road test, checking everything from acceleration to braking, steering, and turn signals. How it works conceptually often involves automation tools that control a web browser, mimicking a user's clicks and inputs, and verifying the expected visual outcomes and backend changes. Effective teams build comprehensive test suites, running them automatically every time a change is made to the code. This practice, often part of continuous integration, CI, which we'll touch on in the next chapter, provides a safety net against regressions and fosters confidence in making changes. Why optimize for performance? The need for speed and efficiency. Testing tells us if our application works. Performance optimization tells us how well it works. A slow application is a frustrating application, leading to lost users and potentially higher operational costs. Analogy: in our restaurant, customers expect not just delicious food, but also timely service. A long wait time, even for the best meal, leads to dissatisfaction. An efficient kitchen and wait staff ensure optimal customer flow. Performance optimization involves making your application faster, more responsive, and more efficient in its use of resources, like memory and CPU. Here are some key conceptual techniques. Caching, storing frequently accessed information. Concept: instead of fetching data or regenerating a piece of content every single time it's requested, caching involves storing it temporarily in a readily accessible location. When the item is requested again, the cached version is returned, saving computation time and database calls. Analogy: a chef having popular ingredients pre-chopped and readily accessible at their station, rather than running to the pantry every time. Or pre-baking popular pastries so they are ready for quick serving. Types: in-memory caching, fastest, stored in the application's memory on a single server. Distributed caching, shared across multiple servers for scalability. Asynchronous programming, async await, not just waiting around. Concept: many operations in a web application are inherently slow because they involve waiting for external resources such as database queries, calling external APIs, or reading from disk. Traditionally, these waiting operations would halt the execution of the current task, blocking the application thread. Asynchronous programming, using keywords like async and await in C#, allows your application to start a long-running operation and then release the current thread to handle other tasks while it waits for the operation to complete. Once the long operation finishes, the original task resumes. Analogy: a chef doesn't stand idly by while water boils. They put the water on, then turn to chop vegetables, prepare sauces, or take other orders. When the water boils, they receive a notification and return to it. This maximizes the chef's and the application's productivity. Benefit: improves responsiveness and scalability, especially under heavy loads, by ensuring that your application's threads are always working on something productive rather than waiting idly. Efficient database queries, being specific. Concept: when interacting with databases via EF Core or raw SQL, it's crucial to retrieve only the data you need. Fetching entire tables when you only need a few columns or running redundant queries can severely impact performance. Analogy: if a customer orders a specific ingredient, you wouldn't bring out the entire pantry. You'd retrieve only that ingredient efficiently. Practices: using select statements with specific columns, filtering data as early as possible in the query, and ensuring proper database indexing. Resource management. Concept: properly managing memory usage, disposing of resources, like database connections, when they are no longer needed, and avoiding memory leaks are critical for long-term application stability and performance. Monitoring. Keeping an eye on things. Even with diligent testing and optimization efforts, real-world performance can vary. This is why monitoring is essential. Using tools that track your application's response times, error rates, CPU usage, and memory consumption in a live environment allows you to identify bottlenecks before they become major problems. It's like having a restaurant manager constantly observing kitchen flow and customer satisfaction metrics to ensure smooth operations. By embracing a culture of testing and continuously seeking performance improvements, you ensure that your ASP.NET Core application is not only functional, but also a high-quality, efficient system that delights its users. With our application proven robust and efficient, the final step is to make it available to the world. In the next chapter, we'll explore the various ways to deploy your ASP.NET Core application. Chapter 12. Sharing your creation. Deploying your ASP.NET Core application. We've journeyed through the entire process of conceptually building an ASP.NET Core application, setting up the environment, understanding its structure, defining its communication language, building its logic and UI, handling data, implementing security, and ensuring quality and speed. The final, exhilarating step in this journey is deployment, taking your meticulously crafted application from your local development machine and making it accessible to users around the world. Think of it as the grand opening for your restaurant. Your kitchen is set up, your menu is perfect, your staff is trained, and you've had successful dry runs. Now, it's time to open the doors for the public, scale up your operations, and serve your customers. What is deployment? Deployment is the process of packaging, configuring, and installing your application onto a server or a network of servers that is connected to the internet and can host your web application. This server will then act as the primary, public face of your digital restaurant, ready to receive incoming HTTP requests from browsers and other applications. Key considerations before opening your doors: deployment preparation. Before you open, a few crucial adjustments are typically made. Configuration for production. Your app settings JSON from Chapter 3 comes into full play here. Your application needs different settings for the live environment compared to your development machine. For instance, the database connection string will point to the actual live production database. Logging levels might be set higher for critical errors and lower for debugging information, and security keys will be securely stored. Security hardening. While we built security into our application, the deployment environment itself needs to be secure. This involves ensuring the server is patched, firewalls are configured, and unnecessary services are disabled. Optimization packaging. Your application code needs to be compiled and packaged into an efficient, optimized format. ASP.NET Core makes this easy, creating a lean set of files ready for deployment. Hosting models. Where will your restaurant be located? Once your application is ready, you need to decide where it will live. ASP.NET Core offers flexibility in hosting: on-premises servers, traditional location. This involves hosting your application on physical servers or virtual machines that you own, manage, or rent in a data center. IIS, Internet Information Services, Windows. For applications deployed on Windows servers, IIS is a very common choice. Think of IIS as a highly experienced, professional maître d'hôtel. It sits at the front, receives all incoming HTTP requests, handles static files very efficiently, acts as a load balancer, and then intelligently forwards the more complex requests, those requiring ASP.NET Core processing, to your running ASP.NET Core application. Kestrel, ASP.NET Core's built-in server. Every ASP.NET Core application uses Kestrel as its internal web server. Kestrel is fast and cross-platform. However, in production environments, Kestrel is typically run behind a more full-featured server like IIS on Windows or Nginx/Apache on Linux. Kestrel is like the efficient expediter working inside the kitchen, managing the flow of dishes from the chefs to the wait staff. But IIS/Nginx is the public-facing establishment that handles all incoming foot traffic and initial customer interactions. Cloud hosting modern, flexible locations. Cloud computing has revolutionized deployment, allowing you to leverage vast, scalable infrastructure provided by companies like Microsoft Azure, Amazon Web Services, AWS, or Google Cloud Platform, GCP. Platform as a Service, PaaS, Azure App Service, Concept. This is a highly popular and convenient way to deploy web applications. The cloud provider gives you a fully managed platform where you simply deploy your code, and they take care of all the underlying infrastructure servers, operating systems, networking, scaling, patching, etc. Analogy. It's like renting a fully equipped modern kitchen. You bring your recipes and ingredients, your application code, and the landlord cloud provider handles all the plumbing, electricity, maintenance, cleaning, and even helps you expand or shrink your kitchen space as demand changes. You don't worry about servers, just your application. Benefit: great for developers as it significantly reduces operational overhead. Containerization, e.g., Docker and Kubernetes. Concept: this is changing how applications are packaged and deployed. A container, like a Docker image, bundles your application code, its dependencies, and everything it needs to run into a single, isolated, portable unit. Analogy: imagine your entire restaurant kitchen stoves, fridges, ingredients, staff is packaged into a standardized, sealed shipping container. Wherever that container goes, it can be unpacked and run exactly the same way, whether it's on a developer's laptop, a test server, or a cloud server. This ensures consistency across environments. Kubernetes: for managing many such containers, you use Kubernetes. Kubernetes is like a massive, automated dockyard manager that can orchestrate, scale, and manage hundreds or thousands of these restaurant containers across a fleet of servers, ensuring your business can handle any customer rush. Benefit: provides immense portability, scalability, and consistency. Serverless, brief mention. Concept: for specific scenarios, you can even deploy individual functions or small pieces of code that run only when triggered by an event, like an HTTP request or a file upload, without explicitly managing any servers. Analogy: selling just one specific signature dish from a vending machine, where the kitchen is only activated when someone pushes a button. Automating the grand opening. Continuous delivery, CI/CD. Manually deploying your application can be time-consuming and error-prone. This is why modern development relies heavily on continuous integration, CI, and continuous delivery deployment, CD, often referred to as CI/CD pipelines. Continuous integration, CI. Every time a developer commits changes to the application's source code, an automated system like Azure DevOps, GitHub Actions, or Jenkins automatically runs your tests, unit tests, integration tests, and builds a deployable package of your application. This ensures that new changes don't break existing functionality and that your application is always in a releasable state. Continuous delivery deployment, CD. Once the CI process creates a valid package, CD automates the process of deploying that package to different environments. Delivery. Your application is ready to be delivered to a testing or production environment, often requiring a manual button push to move it live. Deployment. The application is automatically pushed live to production without manual intervention. Analogy. This is setting up an automated factory for your software. Whenever a new car part design is approved, the factory automatically tests it, builds the necessary components, and integrates them into the assembly line. With continuous deployment, new cars featuring those components automatically roll off the assembly line and are sent to dealerships. CI/CD pipelines allow teams to deploy new features and bug fixes rapidly and reliably, reducing the risk of human error and speeding up the delivery of value to users. Post-launch strategy, monitoring, and evolution. Deployment is not the end. It's the beginning of your application's public life. Once deployed, continuous monitoring, as discussed in Chapter 11, is essential to track performance, identify errors, and ensure your application is healthy and responsive. Just as a restaurateur constantly monitors customer feedback and sales, a developer continuously monitors their live application's metrics. ASP.NET Core makes it incredibly easy to move from idea to production, whether you prefer traditional servers or embrace the power of the cloud. The framework's flexibility and the robust surrounding ecosystem provide all the tools you need to share your creation with the world. You have now conceptually walked through the entire process of building an ASP.NET Core web application, from its core fundamentals and architecture to its ultimate deployment. The web is a dynamic and ever-evolving landscape, but with the foundational understanding gleaned from these chapters, you are well equipped to bravely explore the world of modern web application development. The knowledge contained within these pages provides the map. The journey of building truly amazing digital creations now awaits you.